workshop, and thanks for the opportunity to speak here. And I'll go straight to the topic. So I'll actually talk about the existence of AC spectrum on trees in general. So it started with the Betty lattice when Abel Klein proved the existence of AC spectrum in '98, and afterwards, in about the same time, Eismann, Simpson, Wörtel, and Frosse, Hassler, and Spitzer proved the same thing, the existence of AC spectrum on a Betty lattice. Now, I will not emphasize on the first two papers, but Richard Frosse is actually my advisor, so this is the main thing I'm going to talk about. So they used the geometric method to prove the existence of AC spectrum on the Betty lattice. And I went on from there, and I tried to use the same type of ideas for other type of trees. So what I first did was I perturbed the tree a little bit. So what happened is I added an extra loop to it. So I had a weight P, and if P was 0, then I had the original Betty lattice. If I put another weight, then I'm going to have the other branching. For small p, I check out and I notice that there is still AC spectrum. Well, therefore, I decided, well, what if I make P1 and I get rid of the Betty lattice and I actually get something that has a broken symmetry. So I don't have the same number of nodes on both edges of the tree. And it turned out I still have AC spectrum. So the general version of it is when I can add a random number of nodes on both sides. So, you know, M on the top one and on the lower one. The original Betty lattice doesn't actually have to have connectivity 2. That means that it doesn't have to have 2 branching on each node originally. I can have from here k branching coming out, and on each of them different number of extra nodes.
So it looks like marriage of one-dimensional chains.
Yes, but it's finite.
Yeah.
So all my numbers are finite.
You have the same branching at every node, or can you also vary that?
No, probably a tiny bit, yes. But the main trick is that I'm relying on the self-symmetry of the tree. It's not so obvious on the big one because I was kind of lazy to draw all of it. But on this one, it's obvious. We'll see later on that this copy. So, okay, if I cut the top here, I'll draw a picture. So on one version of it, what do I have? I have a node. I branch up once, twice, and once down, right? Well then, if I go from here and I make it again, I add another thing, and I add another thing, and so on. It goes to infinity. So it's basically self-similar. The thicker version, if I cut everything else, I still have the same tree. If I add more, I add 2 copies of it and I connect them, I still have the same tree.
So how many of these points in between you allow?
As many as you'd like.
Any finite amount?
Any finite amount.
I just try to think.
So
it will be long pieces along which almost exponentially the function on them should decay because it's practically one-dimensional system. And then still it branches, and therefore it
at infinity.
So it will be some competition between two effects.
Well, the thing is, we'll not care so much about the competition, because what I will do is I will start at any point on the graph and trace the Green's function back to the origin. So in most cases, you start from the origin and you keep on going the other way. Well, I'm going to go backwards. I start somewhere and I go back to the origin.
And what is the statement for any finite p? What you'd like to do?
Oh, that is the statement. That there's an interval where, with probability 1, I have AC spectrum.
For any finite p?
Who's B?
For any finite number of
yes,
how
yes,
M,
yes.
M.
M and yes, for any finite number of them, yes. And
the AC component probably shrinks as you make
M
bigger.
longer.
the component gets, spectral range of the AC component gets smaller.
I will still have 3 intervals depending, okay, so it will shrink probably if I have lots of branching and lots of numbers, but if I, no, actually no, I will always have 3 intervals. They will shrink probably, but there are always going to be 3 intervals in which I can have AC spectrum. Because I'm going to go over the proof, so you're going to see like the main ideas, and you'll see where it comes from, the actual interval of the AC spectrum. So let's look at this case and see what happens. So what do I have? I have a Hilbert space, the normal thing, defined from my graph has vertices and edges. So phi is defined from the vertices to C with the normal condition. I'll call my graph F. Finite. I have the discrete Laplacian.
Square, I suppose.
Square.
Sorry. I have the discrete Laplacian. At some point x, I'm going to call this particular one x. And this is going to be my y, and the generic one is going to be a u. So this is going to be the sum at all neighbors u, with the distance between u and x being 1, of phi x minus phi u. Yes? Excuse me, F? F is my tree. Okay, so I'm going for F.
Anyway, x would be in D.
Sorry?
X is in V in the sum rather than X is in F.
Oh, okay, yeah. And it's probably with a minus in front, but the order doesn't particularly matter. And a random potential Q, also from V, at each side X, they're going to be IIT with some density, probability density function mu of X dx. With Q, fairly small, so it concentrates around 0.
So you even allow nu to be things like discrete measures, sums of delta functions.
It works for the Bernoulli. And what happens? Okay, so I have my Laplacian. Oops. And what am I looking for? Well, I'm looking for a condition to prove AC spectrum. And first of thing, I'm going to look at the Green's functions, because probably that's going to help me. And we'll see how it's going to help me. And the Green's functions, the cube denotations, so gx, depending on lambda, I'll write in general as being x h minus lambda minus 1x. I think I'm consistent with the notation before. And I'm going to call it hx. That means the Green's function for the truncated graph. So everything from x forward. And using the transfer matrix formalism that I'm not going to insist on, that means writing the big matrix for the Laplacian and using, like, the inverse formula, like the Schur formula for matrices to compute the inverse, we can get a recursion for formula for the Green's function. And what that looks like is the Green's function at the origin is going to depend on the potential here, the potential here, and the Green's function at the 2 points x and y. And what do we have? So we have that the Green's function at the origin is going to be the Green's function at x plus lambda plus 1 minus q1, which is the potential in between the two of them, to the minus 1 plus the Green's function at y plus lambda minus q2, everything to the minus 1. Now, there is a shift between the expression here and the one here, like this is lambda plus 1 and this is just lambda. And the shift comes from the fact that I have different connectivity, right, at x and at the node in between. One is 3 and one is 2, so when you write the Laplacian, you can't get rid of the diagonal completely because it's a different constant on the diagonal, so you have this shift coming up. So what do we have? We have this pretty much a function that I'll call it phi that goes from two complex numbers that are probably going to be in the upper half plane. So I'm going to have two copies of h. I'm going to have two copies of r because I have two q's coming up. And I'm going to have another copy of h for lambda. That's complex. And it takes actually values still in the upper half plane. And I'm going to express this function for you. So it's going to be a phi of two complex numbers, Z1, Z2, two q's, q1 and q2, and a lambda, which is minus 1 over Z1 plus lambda plus 1 minus q1 plus lambda plus, Z2 plus lambda plus minus q2.
Where did the minus 1 on the top come from?
Oh, it's to the minus 1.
No, but that's your 1 over that.
Oh, I guess I have minuses, sorry.
Oh, okay.
This is basically definition of
Oh,
Z,
all right, fine,
right?
okay.
Of phi.
No, these basically.
Okay, so Z is actually the Green's function, is gx
Yeah.
of lambda, and Z2 is going to be gy of lambda.
And this is a mapping.
Yes, and this is the mapping that takes me from the two Green's functions to the one beforehand. So I'll actually point out that.
Why 2? Because your branching is 2. So it would be 3.
Yes, because I'm going for the smallest version, so the branching is just 2. But it's actually a fractional linear transformation. It doesn't matter how many branching I'm going to have, as many times that I flip, it will still be a linear fractional transformation, which makes things nice. And this is going to be the phi of Z1, Z2, and so on. It lives there. So now let's go back at my function phi. And as observations, if I make Z1 equals Z2 and Q's 0, and so shall I write bigger the characters? Yes.
Is there some reason why the resultant are not
Yes, because of the extra node on one side. If I would not have the node, I would actually have, well, I'll write it here. The phi would actually be just minus 1 over Z1 plus Z2 plus lambda minus Q. The Q2 in the picture, that's one of the origin, right? Because Q1 is going to completely vanish, right? And if I don't have the branching 2 and I have K, then I would have a sum here for all of them. If I add M nodes on one side, then I will apply this transformation over and over again to one set. So if q's are actually 0 and z1 equals z2, equals some z, then my phi is a contraction in the upper half plane. Which has a fixed point. So if I solve for it equals z, I will get z lambda, which in fact is the Green's function for the free Laplacian on the tree.
Fourth order equation.
Sorry?
Yes. So it will be fourth order.
Third order, actually.
Huh?
Third order.
Third order.
Third order, yeah. So this will give me a range for lambda. Well, I mean, I'm asking for the z lambda to be in the upper half plane. I will not always have the solution in the upper half plane for my third order equation. So asking for that determines where lambda can be. And that gets some intervals for lambda. I think I have some numbers. If you're interested in the actual numbers, it's like some minus 2.9. There's something here between -1 and I think 0.88. And it goes to 1 point something on the other side. That doesn't particularly matter, 1.3. So basically, those are the intervals. So I have a branch here, another strip here, and another strip here.
Sorry, what are you drawing here?
So on the real axis, this is the spectrum for the pure one. Well, yeah, so the non-random
It
version,
consists of
just the
three
Laplacian. It consists of 3 intervals, in fact.
And there's space in between or just divided by a point?
I'm skipping the points. Yes, it's just a point.
Oh.
But I don't know how to do the.
There is finite depth.
And at the point the density states goes to 0, or what's happening there? What's the significance of these 2 points?
Oh, so well, in order to look for the, in order to have the fixed point in the upper half plane that would give me the Green's function, I will actually have a condition on lambda.
So it's
the actual condition.
It's basically, you can write a profile of density of states in this, right?
Yeah.
Say vanishing on this, vanishing it or going to infinity. Something should happen on this boundary. So what is profile? Or it's not important?
For me, it's not.
In one dimensional case, it diverges. Usually it vanishes. So
it's a very weird behavior actually at this one. But yeah.
Yes, but the spectrum is a closed set, so these points are still in the spectrum, right? So what we are drawing is something basically of space, it's not just characteristic function of the spectrum.
Okay, so in order to have
You say that for those lambdas on the real line, except for these 2 points and outside of these intervals, you have the solution for this lambda.
no, I'm saying inside the intervals, not outside intervals. So the fixed point of this equation is actually the Green's function for the free Laplacian. But in order to actually have this fixed point, so to have the bounded Green's function, I need to have a condition on lambda. And the condition of lambda from my third order equation, polynomial, gives me these intervals. Okay, so only if lambda is in these intervals, I do have a fixed point in the upper half plane.
So as you go to the boundary, your fixed point approaches the real axis. So the
Yes.
fixed point in the upper half plane means there's an imaginary part to the solution, a finite, positive imaginary part to the solution, and that imaginary part goes to 0. So it sounds like that it's supposed to vanish.
So basically, I will look at lambda in this strip, right, where the real part of lambda is in this interval f. F is the one on the real axis.
So you're going to prove that this fixed point is stable with respect to small disorder. Is that
Yes.
the strategy?
Yes. So the point is that the probability density function is going to, accumulate somewhere near the fixed point of the free one. So it's not going to go, the boundary is going to have no weight on it. That's basically the idea.
But it's probably, it doesn't mean that, say, support of the density is the same as in pure case. Maybe it probably.
No, that's one point in the for lambda fixed.
This is support of your spectrum for pure case, right?
Yes, it's smaller.
But this will be larger when you add disorder.
No, it's going to be smaller.
Smaller, sure.
Well,
It's
I
a
imagine
little
where she
smaller.
can prove something.
Ah,
I mean, she now has to analyze the situation
okay.
and probably prove stability of this
So-
recursion. And in order to do that, she probably has to shrink it somewhat.
Okay, so
And make it
but
close,
in
because
fact,
I'm
proof
going to
can
have a
be
closed interval,
carried
right,
out
for the
in
spectrum.
Smaller.
That's-
And I just,
All right, where was I? And, imaginary of lambda is going to be, less than some epsilon. That's the height of my interval here. Okay.
Sorry, can I just quickly ask, these numbers, this is for Bernoulli variables, yeah?
No, IIDs.
IDs, of what distribution? So is this a particular case, these numbers you've written down?
oh, but this is without any disorder.
That's without disorder.
Oh, this part. Okay, yeah, this is without.
So
the
Q
Qs,
is,
the Qs are 0.
ah, okay. Sure, 1, yeah.
And did I get it right, that your tree has exactly the same number, so in this branching you add exactly the same number of nodes in the upper and lower branch in every branch. So
Yes, it stays the same.
yeah, this is M and N on your transparency is really always the same.
Yes, it is.
Oh, okay.
And so the
It's a
spectrum is not
self-similarity that I have to
Yeah.
preserve. Yeah.
So the spectrum is not symmetric.
No. Because the graph is not symmetric anymore, I assume. We have some sort of a relation to it. It is symmetric if you keep the symmetry, right? So if you add the same number on both sides, like, m equals n there, then it is. And basically, if I can prove that the expected value of my Green's function to some power 1 minus p, taking the sup over lambda in my strip that I just defined, is finite, then I know that I have AC spectrum. So Barry-Simon actually proved the deterministic version of the result, and then, with small adaptations, it actually can be probabilistic. There is something similar in Abel Klein's paper too, but he has actually 2 here. And my p, that's actually important, is between 0 and 1. So that's what I'm looking for. And it would be actually enough to prove that the expected value of some weight function of the Green's function is finite. Would be the same as proving that the absolute value is the expected value of the absolute value would be finite. And since I have to connect to the fact that I have the free Laplacian with my Green's function on the free Laplacian, I'm going to look at the distance between the Green's function of the free Laplacian and the Green's function for the random one. So I will look at some function CD that will depend on Z and Z lambda, defined as being the absolute value between Z minus Z lambda squared over imaginary of Z. Where when I plug in, actually, instead of Z, my Green's function, it will be the distance between the Green's function for my graph and the Green's function of the free Laplacian on the tree over the imaginary part of the Green's function. So it will blow up on the boundaries, right? If imaginary part goes to 0, this will blow up. If z just goes to infinity on the other side, it's still going to blow up. Not sure if it has any sort of importance right now, but it is in fact a distance, a cosine of the hyperbolic distance in the upper half plane. So actually, we have just to look at the expected value of the CD, so cosh distance of the power 1 plus b of the Green's function. And in the definition, I will actually not write the z lambda anymore, because I'll have too many variables sitting around. And what is this in fact? Well, it's the integral of the CD to 1 plus b of my z d rho z. Now, another advantage of having IIDs is that the actual probability density function of the Green's function is the same at all my similar sites, so at x, y, or 0.
Do we know what rho is yet?
It's the probability density function for the Green's function.
But you'll have to compute it
You have to compute.
from by some fixed point from the recursion relation, I suppose.
Or maybe,
How do you get?
or
Maybe
maybe
it's
she
asking
doesn't.
how are you going to get p rho?
Explicitly?
Well, not explicitly. It's
What are you going to do with the rho? This is the question.
maybe we just wait and see.
Okay. So, because I have my phi, this is going to be the same thing as phi of the expression. And now I will have 0 of z1, z2, and that's it. And this would be over 2 copies of H and 2 copies of R. And from here it's just basically a computational trick for a while. So I will just symmetrize. My phi is not symmetric, as we noticed. And if I don't symmetrize, actually things don't work well. So I'll actually symmetrize in Z1 and Z2. So this is the same as writing 1/2 because the moment I integrate, it shouldn't matter which one is first, which one is second. And all the integration factors coming afterwards. And now the main point is I want to compare this relation with itself to show that it's bounded. So what I do, well, I create what I'm looking for, basically. And I keep the same bracket from here. and I divide it by the sum of the CDs, and of course I have to multiply by it because I have no choice. Now, the bracket that I've actually skipped here is the only part that contains Q1 and Q2. So I can split it in two now. So I have one integral that has my fraction here. I'll call this phi 1 when z1 is first, and CD phi 2 when z2 is first, over the other sum. And the leftover is just the z1 and z2. And now, well, there are some points where I have issues here. So if z1 and z2 are actually the fixed point, I'm going to have 0 over 0, so I would have a problem. So basically, before I do this step, I will take a compact set out where I take the points z1 and z2 being z lambda, I take it out. I integrate separately, and that's going to be finite because it's over a compact set. And I'm just looking here at the complement of it, where k is going to be in H cross A. So this will be over the complement where I'm safe with my fraction, plus the constant, and the same thing here. Now if I prove that this term is, let's say, less or equal 1 minus epsilon, I'm done. Because basically what it tells me that my expectation of the Green's function is less than equal 1 minus epsilon itself. Plus a constant, which implies that the actual expectation is going to be less than equal C over epsilon, so it's finite. So the part that I should probably skip is to prove that this expression here is 1 minus epsilon. Basically the way it goes is for Q1 is Q2 equals 0 is going to be strictly less than 1. And then when I integrate for all Q's, it will still say 1 minus epsilon, or an epsilon over 2. And to prove that actually less than 1 for Q equals 0 is not particularly short, because you have to look at all the boundaries, and there are points where there are some blow-ups needed and so on to actually show that this expression, so-called the mu2, let's call it, is strictly less than 1. And since I proved that the expected value is finite, I can conclude that there is AC spectrum. Now, this part is actually shorter in this version than for the body lattice or a symmetric tree. So the broken symmetry that I actually have to add it back on in a way still preserves still simplifies it. And why does it so is that my phi here, that would look like this, will actually be an isometry on the diagonal. So this one of Z and Z is actually an isometry, which will preserve the distance. So the quotient there will be 1 on the diagonal.
I hope this epsilon that's in this equation is not the same. It's not the same as the one that you used to define the R, is it? Script R.
No.
Okay.
I'll call this one epsilon tilde.
Very worried about that.
Yeah, I have too many epsilons, I guess.
So in fact, it helps to have this exercise and so on.
The broken symmetry actually helps, yeah. Well, and so if you don't have the broken symmetry, right, as I said, on the diagonal, when the two values are equal, you actually have an isometry. So the distance between, the distance between one fixed point and the other one will basically stay the same. So I will not get this factor being strictly less than 1. And then what you have to do to still break the symmetry is basically go back one more step on one side of the graph, right? So instead of going just, okay, I'll go for this one. So instead of going just one node back on one side, only on one, you just go an extra one. And that breaks the symmetry automatically. But it's computationally harder in a way, because there are a couple more integrals going on. Questions?
So this whole thing hinges on there being self-similarity in the graph, right?
Yes.
So I guess can you extend it hopefully to just any kind of quasi-transitive tree? So any tree where there's only a finite collection of nodes, and then any node can be mapped by an automorphism to one of those groups.
Probably yes.
Because that'd be nice.
As long as the group is finite.
Yeah, exactly. Yeah. And do you think that the result is wrong in the case where you don't have self-similarity, or just that the proof technique won't work?
The proof technique might not work.
Do you think the result is right? Any tree should have.
I should probably not say any opinion on that. But no, I mean, the result might not actually work because of the, I mean, okay.
We expect it to be true. We expect AC spectrum in high enough dimension and weak enough disorder. This is what we're learning from Tom Spencer's general description. And you can ask, in what sense does this correspond to high dimension? And the rough answer is that in high dimension, the contribution from loops, the higher you go up in dimension, the contribution from loops will be reduced. Because the phase space or the possibilities grow, and so there's just the a priori probability to go around and come back to where you started from, it goes down. So in that sense, something that doesn't have loops to begin with somehow reflects or corresponds to high dimension. So based on that heuristic reasoning, we do expect AC spectrum, but it can only be proved when the whole thing, or the strategy here is that you have this closed formula for the Green's function, and you just work hard enough with it and you produce some answer, produce a theorem.
We're trying to actually add some connections in between the nodes and see what happens, but I can't say anything yet. I mean, the next idea is to use some sort of a tree that basically can translate it into the lattice, right? And then try to see what happens.
So are you trying to say you're trying to add loops? Or
Yeah, I'm adding loops, yeah. So basically what
how are
I'm...
you going to make progress then?
Well, it depends on the weight on... So I'm going to add an extra edge, right? So when you start and you have the connections, and we go like this, and at the next level you have them again, right? So what I'm going to do, I'm adding like an extra edge in between that has some weight.
Everywhere.
Yes, no.
Or only
Here,
No, I bet you will only have
Still-
loops of finite size.
Yes.
There will be a
Right.
bound on the
Oh.
maximum
Oh.
circumference going around.
and then the same thing at the next level, because what
You
will...
do it at every level? Or
Yeah.
It's
I'll do
kinda
it at every
decoration.
level, because the
But
thing
all the
is,
loops will have size, whatever, 4.
for really high weight, if these two nodes are gonna, shrink into one, and it's gonna look like the lattice actually. If you shrink all the nodes, it's gonna be like. So that's the point of trying it, but
Did you think about making the number of additional vertices random? So having a distribution between 1, you set from 1 to n, and at each point you decide how much additional vertices you will have?
no, I have not thought of that. And actually, if you have infinitely many, it's pure point.
But,
Yeah, well-
I want to
Because it's
ask,
like the
there
Z,
should be
yeah,
some
yeah.
crossover. So if you just let m go to infinity in some way,
Yeah, then it will actually be pure point.
you
It was proved.
natural.
Yeah, that's expected.
I didn't get the point.
Good.
Can you repeat the point?
If you just make these long one-dimensional branches longer and longer, they will dominate everything. It will be like one-dimensional. Okay, intuition, I think like this.
So yeah, if you keep the m and n equal,
Yeah,
and you
but
make them
they dominate because
going
you
to infinity.
far before you branch. Yes, it probably is a matter of linear, but
So where are we? Was that the end of the talk?
Yes.
Let's thank her.